So now we're going to continue with another horizontal transformation problem. And what we're going to basically do is we're going to try to graph g of x equals to f of x minus 3. Now you saw in the previous problem we did x plus 2, and we saw that that was a horizontal shift to the left by, in that case, 2 units. Now we're going to do f of x minus 3. We're going to claim that it's going to be a horizontal shift to the right by 3 units. We're going to show that now, and then at the end we'll conclude with what that means. And by the way, I hope that you, and by the way, I want you all to notice that, like, my argument about why it shifted, you don't necessarily have to understand it on a first viewing, but I want you to see, but I do want to show it to you as a, for completeness. And also, but to apply it to the problems, you'll see that we just need the conclusions. But I don't want you to hurry through the videos because I also want you to internalize these ideas of thinking about these problems. Yes. So without further ado, let's begin. So we're using our same toy function here, and so let's see this. Okay, so first I'm going to draw my x-axis and y-axis in. Okay, this is going to be my x-axis, and this is going to be my y-axis here. Okay, and let me see here. I'm going to do, let's say, -1. Oops, let me not make them so tight. Okay. -2, -3, -4, 1, 2, 3, 4, 5, 6, 7, 8. Okay. And look, underneath it, as I did before, in this case I'm going to draw it underneath. I'm going to draw what the numbers would be if it was x minus 3. So kind of like underneath the graph, I'm going to draw what the numbers would be if they were x minus 3. So for example, -4 minus 3 would be -7. -3 minus 3 would be -6. -2 minus 3 is -5. -1 minus 3 is -4. 0 minus 3 is -3. 1 minus 3 is -2. 2 minus 3 is -1. 3 minus 3 is 0. 4 minus 3 is 1. 5 minus 3 is 2. 6 minus 3 is 3. 7 minus 3 is 4. 8 minus 3 is 5. So in other words, this is where we're going to graph the thing. But these are the, imagine that f can see the number that you're putting into it. The f cannot see the x minus 3. The f just see what x minus 3 evaluates to. And if you look here, these data points that f is looking for to graph occur, you see this -2 to 3, they occur here in this graph from 1 to 6. And so you can already see what would have been here under our original, where f would be graphed here from -2 to 3. It's going to be graphed here from 1 to 6. You see? And so, in fact, just looking at that, looking at the comparison, I can already graph in my g. Right? Because I know that here, for -2, right, which is what the f is going to see here, it's going to be 0. For what -1 would be here, it'll be 1. The next one will be 0 again, then -1, then 0, and then 1. And it'll be graphed like this. Okay. So what I want you to notice here is that these numbers correspond to what the function f is going to see for these x values, right? Which are the x values that g is going to have inputted, right? And so what I'm also claiming here is that if I make a table, right, like let's say this is my x and this is my g, I'm claiming that at x equals 1, g is 0. At x equals 2, g is 1. At x equals 3, g is 0. At x equals 4, g is negative 1. At x equals 5, g is 0. And at x equals 6, g is 1. Okay? Now in this example, I'm going to go through each of these calculations one by one just to completely convince you that this is correct before we go to the generalization. Okay? Yes. Okay. So let's do that here. So first of all, I'm going to plug in x equals 1. I know that g of 1 is going to equal to f. What does it equal? F of 1 minus 3. What is 1 minus 3? Negative 2. So that will equal f of negative 2. We know what f of negative 2 is. F evaluated at negative 2 is 0. That is 0. So I can see that this first point that we claimed we had originally claimed that g of 1 was 0 based on our purely geometric argument here. And what we have just shown analytically, that is by using the formula, by using the definition of g, we saw that matches up. G of 2. G of 2 is going to be f of 2 minus 3. What is 2 minus 3? Negative 1. That's going to be f of negative 1. From our table for the f, we see that f of negative 1 is 1. Right? Because for the input negative 1, f evaluates to 1. G of 3. That corresponds to f of 3 minus 3, which is f of 0, which corresponds to the y value 0. So that one's also confirmed. Now, let me come over here to let me erase those to complete, or actually I'll complete the table down here, and then I'll erase them so you can get the graph very nice. So g of 4 is going to equal to f of, so g evaluated at 4 is equal to f evaluated at 4 minus 3. What is 4 minus 3? 1. So that'll be f evaluated at 1. And we know from our table that f evaluated at 1 is negative 1. The next one will be g of 5. G evaluated at 5 is equal to the function f evaluated at 5 minus 3. What is 5 minus 3? That's 2. That means that this is going to be f evaluated at 2. And we know from our table that f evaluated at 2 is 0. And finally, the g evaluated at 6 is equal to f. The g evaluated at 6 is equal to f evaluated at 6 minus 3. What is 6 minus 3? That's 3. So it'll be f evaluated at 3. And of course, f evaluated at 3 is 1. So we can see that each point on this table that we arrived at through purely geometric means can be rigorously calculated using the definition of our g. Okay? And of course, relying on the small function table we have for our f. Okay? Now let me erase these calculations. And so now I'm going to write down what our conclusion is. So in general, okay, if we have a function g of x that is equal to a function f, that is equal to f evaluated at x minus h, where h is some positive value, that is, if g of x equals to f of x minus 3, if g of x is equal to f of x minus 4, if g of x is equal to f of x minus 1,000,000, for example, then that will correspond to a horizontal shift to the right by h units. Yes. And there you go. I hope that you've enjoyed this video, and I'll see you again soon. Thank you.